A very good morning to all of you. First of all, thank you for attending our webinar that is organized by Faculty of Engineering, University Technology, Malaysia. My name is Lux Research. I'm an academic staff from School of Chemical and Energy Engineering, UTM. Today, we are very honored to have Professor Stephen Gray from Victoria University, Australia, to deliver his lecture here. A brief information about the research collaboration between UTM and Victoria University. Both universities started to collaborate since 2015 when I received Australian Endeavour Fellowship, in which Professor Stephen was my host supervisor for 4 months. Since then, we have joint research collaborations on the project related to thin film nanocomposite membrane for water applications. Professor Stephen, in fact, he first time visited UTN in 2016, and last year he was one of the premier speaker for our conference organized in Johor Bahru. So without further delay, I would like to invite the Dean of Faculty, Professor Rafiq, to briefly introduce our speaker today. Thank you.
Thank you, Dr. Lawiji, for chairing the session. Assalamualaikum warahmatullahi wabarakatuh. Welcome everyone to our 57th UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering, University Technology, Malaysia. Today, it is my utmost pleasure to welcome Professor Stephen Gray from Victoria University, Australia. A bit about our distinguished speaker today. Professor Gray has had a focus on water and membranes research for over 27 years. He is part of research teams that are working towards commercialization of membrane distillation, have introduced ceramic membranes to Australian industry, and is working to demonstrate membrane integrity monitoring technology. In the field of membrane fabrication, he has projects that span nanocomposite UF membranes for increased abrasion resistance, nanocomposite pervaporation membranes for niche applications, ceramic membranes for desalination, and small pore size metal membranes. In 2013, he was recognized as a thought leader in Lux Research International Review of Water Research. He is currently president of the Aseanian Membrane Society, editor of the Journal of Water Reuse and Desalination, and on the editorial board of Water Research, Desalination and Membrane journals. So that is a brief biography of our distinguished speaker. Here now is Professor Stephen Gray from Victoria University, Australia, with a talk entitled Membrane Integrity for Reliable Water. Professor Stephen Gray, over to you.
Thank you, Professor Rafiq and Dr. Lau, for that kind introduction and words. I think I need to update my bio because I've just realized I've told you I'm the current president of the Aseanian Membrane Society, but that's no longer true. I finished that role at the end of last year, so I'm the past president of the Aseanian Membrane Society, so sorry about that. It's very good to be able to come and give this distinguished lecture. I was fortunate enough to attend Johor Bahru last year and attend the conference there. So it would have been nice to have come back. I really enjoyed my time there, but this is the next best thing I can do, given that we have COVID not allowing us to travel at the moment. What I would like to do is, so I'm just trying to get my screen up. Is talk to you today about membrane integrity monitoring. So in the introduction, you would have heard that this is one of the projects I've been working on and working on for some years now with some of my colleagues who are listed there on the opening slide. So Dr. Marlene Cran and Dr. Eddie Stasevich have been working on developing a new membrane integrity monitoring system, which I'll talk about in the presentation. We also had a collaboration with Associate Professor Joe Jackangelo in the USA on this topic as well. And again, some of the slides relate to that collaboration. And with Professor Michael Duke, Dr. Jessica Lay, and Andrew Groth, we did some work on new type of UF membrane to increase abrasion resistance, and I'll just talk about that one briefly. So what I'd like to do in this talk is outline why water recycling is important, how water recycling systems are managed. So many of you are probably membrane academics, and so may not really understand that well how we manage water recycling systems. So I'll give you an outline of that. And that relates to why membrane integrity becomes important because of the way we manage those water recycling systems. Look at some membrane integrity issues, how they perform during service, some possible approaches for improved integrity performance of membranes, and then talk mostly around the online membrane integrity monitoring process that we've been developing. So why is water recycling important? This is the average temperature across Australia as across a number of years, and you can see from about the 1960s, the blue line there shows that the temperature across Australia has been increasing. And if we do some modelling there, including greenhouse gas emissions in that model, we get the red line. And if we don't have them in, we get the dotted blue line. So some strong correlation there between greenhouse gas warming of Australia, of the planet. And you can see this data goes up to the year 2000, but some more recent data shows that it's actually increasing beyond that. So, and we all kind of understand that the world is getting a bit hotter, but there's some data that underlines that. If you're in Malaysia, you can see the same sorts of trends occurring, so increasing temperature through the years. So we know that the climate of the world is changing. For Australia, what that means is that those red areas are getting drier and the blue areas are getting wetter. So not everywhere gets dry, but certainly in Australia, all the locations there with the yellow dots, they're large urban cities. So they're our main cities in Australia, and they're all in regions that are getting drier. So for Australia, climate change means we have less water available. And again, this data goes up to the year 2002, but we can take the same data, which they don't show in the red and the blue anymore, which is a nice way to present it. It's a green and a brown, but you can see the brown areas are getting drier. So the same trend when we get more recent data as well. One of the outcomes of that is that we get less rainfall in these areas. So this is some data from Perth over here. I've probably seen those messages come up. Sorry about that. So you can see what's happened to the rainfall in Perth. From about the late 1990s, they've had a drop in rainfall, about 14%, and then more recently a drop of 21%, and I think it might have even dropped again. Again, this is a little bit old, this data. What that means, though, in terms of runoff into the catchments, so our reservoirs that we've traditionally relied on for our water, is that when we have a 14% drop, that correlates to a drop of 52% in terms of water flowing into the reservoir, and more recently a drop of 64% water flowing into that reservoir. So our sources of water are becoming less reliable, and that is quite an extreme case, but similar things are happening across Australia in terms of the reliability of our reservoirs that we've traditionally depended on. So the response to that around 2010, or around that period, a bit before and a bit after, is that Australia has built a lot of seawater desalination plants at all their main capital cities, as well as investing in water recycling. But as the climate continues to change and our temperatures get warmer, we expect that these effects will in fact lead to more drying of our climate around our major capital cities. For Malaysia, I was a bit surprised last year when I went to Johor Bahru. I always thought you fairly wet and had a lot of rainfall, which I think you do. But I was told on that occasion that you'd been buying water from Singapore at certain times of the year. So I found that a bit surprising, and so maybe water recycling will also be quite relevant to Malaysia. It certainly will be not just in Australia, relevant not just in Australia, but through many places in the world. You know, the USA and South America have had dry periods, and lots of the world will be investing in water recycling as a result of that. So how do we manage our water recycling systems? And while what I describe you is the case of how we manage water recycling systems in Australia, this is an approach also recommended by the World Health Organization. So lots of places in the world use this approach to managing water recycling. And it's based on a hazard analysis, critical control point analysis, HAZAP. And so what it relies on is that you have some knowledge of the bacterial, virus and protozoa loads in the feed water. So what you're looking to do in this example is make the water suitable for drinking in terms of the pathogen load that's in that water. So you're not removing the colour, it's removing bacteria and virus. And the feed water quality gets influenced by the level of treatment, and depending on your feed water quality that you're using. So if you're using recycled wastewater, then you have to have a very high level of treatment in order to make that water quality suitable for drinking. And what we express, how we express the removal of those pathogens is through a log removal value. And so 1 log removal value equals 90% removal. So we have 10% of the pathogens left in the water. A 2 log removal value is 99% removal. So you've got 1% left in the water. 3 log removal, 99.9%, etc. So when we're thinking about treating wastewater for recycling, for drinking, so to make it potable water quality, we're typically looking at getting an 8 log removal value across the treatment process. So very high rates of pathogen removal that we have to guarantee for the health department in order to get that water recycling system approved. When we use a HAZAP approach, what we're doing is using online parameters to verify that the unit, the water treatment process is working properly, and it's getting the log removal values of pathogens that we require from that unit treatment process. So we end up measuring parameters, water quality parameters that we can measure online, and they're surrogates, so we're not actually measuring the pathogens. So to measure the pathogens, we'd have to take a sample, send it to the lab, and then get the results a few days later. And that's not a good way to operate a water recycling process, because the water's already gone out by the time you know the results of that, the laboratory results. So we want to know online in real time that the water treatment process is working. So we're measuring these water quality parameters online and calculating out what we call a critical control point. And we know that if we're hitting that critical control point, then this treatment process is working properly. So if we think about chlorination, a fairly simple process, our critical control point is the residual chlorine concentration times the residence time. So that's how we understand that if we want a 4 log removal of virus, we have to hit a certain chlorine residual concentration after a residence time of whatever that is. So when we multiply them out, we get a number, and we know these values here from previous research that's been done, and we can say with confidence then that if we're hitting this CT value, we're getting 4 log removal of virus, or 3 log removal, depending on what CT value and what log removal value we need across that unit process, or in this case, the chlorination process. We know that pH and temperature affect the CT value that we require to get the 3 log removal or 4 log removal. So we're having to measure pH and temperature in line. We also know that the residence time is affected by the flow rate, so we measure the flow rate, and then we can measure residual chlorine concentration at the end of that contact period. So we can calculate the CT value from measured parameters online, and from that we can be sure that we're hitting the right correct log removal value required by the health department. So that's an example of how chlorination works. For membranes, we know that that works by size exclusion, and for microfiltration and ultrafiltration, the techniques we use to ensure integrity are the pressure decay test. That's what we typically use, which is really, it measures the bubble size, and typically we're really looking at breaches of the membrane that are around 1 micron in size. So not particularly good for virus, but that's what the industry standard is. And with conductivity, we typically use, with reverse osmosis, we typically use conductivity to calculate a log removal value. And we know that, while we might get 99 or 99.8% rejection of salinity, and we get a conductivity value, so maybe up around 2 at best in wastewater, that's all we can credit the pathogen removal across a reverse osmosis unit with. So we can't actually verify high levels of virus or pathogen removal across a reverse osmosis membrane, although we know it does occur. But we need to be able to demonstrate it online in real time to satisfy the health department. And of course, with things like nanofiltration, which might give us some advantage in terms of pressure drop and energy use, using conductivity is not very good because we're not actually removing a lot of conductivity with nanofiltration. So we get very low log removal values that we can verify online. So when we put a treatment system together that includes filtration, membrane filtration, it might look something like this. So sewage is coming in, we have some biological treatment, and we might get 1 log removal of pathogens across the biological treatment. Media filtration might give you another 1 log removal. Microfiltration, you might be able to claim 2, but for the high pressure membranes, the reverse osmosis membranes, you might get, maybe 1 or 2. In here we've said 0, and then you'll have to have some disinfection after that. So, we have to have quite a few log unit treatment processes in order to reach our 8 log removal value. So we add up all these accredited log removal values to get our 8. But for high pressure membranes, as I said, we know they can remove virus to a very high level, bacteria to a very high level, but we can't demonstrate it online, so we can't be credited with those high log removal values. So what we would like to do is develop an online technique, a membrane integrity technique that we can do online that gives us verification that the membranes are intact, and so we can claim those higher log removal values. And so this might mean we can remove one of the filtration processes. We might be able to reduce the amount of disinfection we do at the end of the treatment process, and we can make the best use of those reverse osmosis membranes in terms of claiming pathogen removal. Okay, so I'm assuming we have quite a few membrane researchers online, and quite often in the laboratory we're using nice clean membranes that we may have made ourselves or we might have obtained from a membrane manufacturer, and we might run them for a couple of days and say that's a long-term test. But in practice, membranes go into the field and they operate for a number of years. So with ultrafiltration membranes, you might be looking to get at least 8 years service out of them before you change them over. And similarly with the reverse osmosis membranes. And there's quite a lot of work goes on by operating plants to extend the life of their membranes, because it ends up being quite a large cost in terms of how it affects the cost of water treatment. But what you can see here is that during the service they get exposed to some quite harsh conditions. So you might be familiar with nice clean membranes in the laboratory, but once they've been in service and you might have been operating with coagulation before the membranes, you can see there's the potential for those membranes to be exposed to very high concentrations of solid particles. So you get abrasion of the membranes, potential breaches may occur, etc. So they, during their life, you have to treat them nicely to actually get that 8 years of service out of them, because the conditions under which they operate can be quite severe. And you can see high levels of fouling occurring on the surface. So these are membranes where we've done some autopsies on them after they've been in service for a period of time. And here's an example of what can happen to ultrafiltration membranes in this case, that are operating on a water recycling plant. And this is a particular example where the membranes were fouling at what seemed to be quite a high rate, not fouling, sorry, showing loss of integrity at over quite a high rate. So when they were new, these UF membranes could claim 3 to 4 log removal of virus based on an MS2 challenge test. So MS2 is a bacteriophage, so it's similar in size to a virus, but it's not as infective like a virus is. So this is what we would typically use to challenge a membrane to verify virus removal. These membranes did not fail a pressure decay test. So these are routinely checked with a pressure decay test when they're in service, but despite that, they were showing a loss of 1 log removal value for virus each year. So in this case, the health department made them do a challenge test with MS2 each year, not just when they were put in, to verify that they were retaining their log removal value for virus. But when they did that, each year they found they were losing one log removal value. So when you have only 3 or 4 log removal values that you can claim, you're seeing that's quite rapid degradation in performance. So when they were hitting, less than 3, it became an issue for them, because now they're not getting their log removal credits over their treatment process. So they're in danger of not being able to operate the recycling plant. And it's a rapid loss of performance for these UF membranes. So we did some work for them using some fluorescent nanoparticles that we made in the laboratory, and this is one of the techniques we use for online integrity monitoring. And here are some of the results down here. So what you see is these fluorescent nanoparticles can be made of different sizes. So this is 55 nanometers, 110, 150, 185. And virus are typically around 30 nanometers, so even a little bit smaller than this. And we can make these nanoparticles that size as well. But with a new membrane, we're getting 100% rejection of all those nanoparticles of different sizes, down to 55 nanometers. Once they've been in service for 2 years, so this is only 2 years of service, the same membrane type, and we have 2 membranes taken from different parts of the operating plant. What we can see is they're all red here, which means there's no rejection at all. for membrane 2, and for membrane 1 we only get partial rejection when they're very large nanoparticles. So even though they were passing the pressure decay test, we had a large change in their pore size distribution throughout their operation. And we could trace this back to some issues with their backwashing system. So they would use hypochlorite in there, but they had some rust in their plant, so they actually had dissolved iron in that backwash water as well, which catalyzes and accelerates the rate of membrane degradation. And so that's what is leading to this larger pore size occurring in a fairly short period of time. So they would have been expecting to get at least 8 years service out of those membranes, but after 2 years they were no longer serviceable for them. They weren't giving them the quality that they required. And this is an example of where online membrane integrity monitoring would be very important and good to know about, because these similar types of membranes are used elsewhere on similar type plants and designs, but it was only some particular issue with this plant that meant it wasn't performing well. So the health department really requires this integrity monitoring online, because sometimes we can't tell when membranes are not performing the way we think they should. Sorry. So quite a lot of membrane researchers make new membranes, but quite often we focus on flux and rejection and not so much on improving membrane integrity. So this is just to give you an example of some work we did on nanocomposite membranes for improving the physical durability of UF membranes in this case. So this was our PhD student, Jessica Lay, and there's some of her publications from that. But really, I suppose I'm just showing this for researchers to think about, maybe one of the things they should be optimizing for is not just rejection and flux, but also wear resistance, or perhaps mechanical strength properties, which can go some way to indicating an improvement in potential integrity of the membranes over their service life. So what we were doing here was making some nanocomposite UF membranes of different compositions, and then putting them through a wear test. So we just make a little loop and then seal them, so then we could do a bubble test, which gives you the maximum pore size, and then we'd put them in a slurry of silicon carbide, and we just put them in a shaker like that. So a very simple test, and that leads to abrasion of the membranes, and we can track the bubble size over time, and eventually when it abrades away, we get an increase in the maximum pore size as measured by the bubble point. So a fairly simple test, and one which we could use then to optimize on the addition of nanoparticles to prevent or reduce the rate of abrasion of the membrane. So we know from nanocomposite research that actually adding nanoparticles to a polymer can actually improve their wear resistance and also their mechanical properties. And what we're doing here is just demonstrating that for membranes as well. So using that technique, we could show that without any nanoclay, so we're adding nanoclay, we could operate for 6 days before we started to see an increase in the bubble size. Once we started to add nanoclay, we got an increase, and it was about 3 times longer that we could do that wear test for before we saw any increase in bubble point. So quite a significant increase in wear resistance. And just to emphasize that, here you can see what happens with the membrane with no nanoclay. This is before we do the abrasion test, and this is afterwards when we have the nanoclay. this is before, after. We can see some wear, but nowhere near the extent of what we see with the membrane with no nanoclay in. So just another approach to doing some improved membrane, improving membrane characteristics, but not focused on flux or rejection, but focused on their mechanical properties and their wear, because we know that will relate back to their service life and their ability to retain integrity throughout their life. And this is just a proposed mechanism as to why that occurs. So we're using PVDF membranes with nanoclay in. When you're getting them wearing and you've got the nanoclay, then you've changed the crystalline phase of the polymer. So it ends up being you have more beta phase present, which is more resistant to abrasion. You can have nanoclay coming to the surface or being exposed at the surface, which is more resistant to further wear. And if you have crack propagation, then the nanoparticles can help stop that propagation of the crack. So there's a few reasons why that can occur. But it's really just highlighting that sometimes we think a lot about flux improvement and rejection improvement, but not so much about abrasion resistance or some of the mechanical properties of the membranes, which can also be important and certainly have a big effect in terms of the cost of treatment if this leads to extension of their service life. Okay, so I'll talk now about some of the work we've done around online membrane integrity monitoring of high pressure membranes. So we've had a number of projects here, some with Water Research Australia, some with the Water Reuse Foundation in the USA, and that was the work we did with Professor Joe Jackangelo. And these are all based around use of some nanoparticles and comparing these nanoparticles with other techniques that we might use, such as dyes. What I showed before with the example of the membrane that had accelerated aging and wear and loss of integrity, we also did some work around membrane integrity monitoring for ultrafiltration membranes, which I won't really go into, but in that case we were making polylactic acid nanoparticles, and they're inherently biodegradable, so they undergo hydrolysis. So you can see that they don't stay as nanoparticles for very long. So it's after 180 days, and that's one of the characteristics that we would like, that the nanoparticles don't foul and they don't stay in the environment for terribly long, because people worry about these things getting into the drinking water. And so we need to have them being biocompatible. Polylactic acid is biocompatible. We're making them fluorescent through the use of curcumin, which is comes from a plant. So we use that anyway in cooking, so it's food grade material. And so these nanoparticles are seen as being very compatible for use if they were to get through to the treated drinking water. It does give us some issues around storing them, but to date they've shown to be very effective in terms of the membrane integrity monitoring, at least in the laboratory and pilot scale work that we've done. But for reverse osmosis membranes, what we're setting out to achieve is log removal value of 4, so we would like, or greater. So we would like to be able to verify that the membranes have a log removal value of 4 or greater in an online environment. We can do this currently using a dye called rhodamin WT. But if we're just relying on conductivity or TDS measurements, then usually we're less than 2 log removal. So as I said previously, this is not a very good outcome for for reverse osmosis membranes when we know they can do a lot better. I also mentioned that MS2 bacteriophage are traditionally used for by health departments to verify the integrity of membranes and other UF membranes and RO membranes, because they're similar size to virus, so that's what's used. We can use other types of tests to verify the performance. So we can do a direct integrity test like a pressure hold test or a vacuum decay test. They need to be done offline, so they can't be done online. And again, they're not very sensitive because you have to go to very high pressures to really get down to detecting a breach that would be the size of a virus particle. So not really useful for us to do an online test and be trying to detect virus removal across the membrane. Similarly, there's some indirect tests like particle counting and turbidity monitoring. They're less sensitive, so we can't get up to the 4 log that we would like. You know, they're getting down around the 2 log again, but we can do some challenge testing. So this is using the MS2 or the Rhodaman WT. So we're having to add something in the water and then detect it on the permeate side of the membrane. And that generally gives us the highest level of log removal value that we can verify across the membrane. The challenge for us was to establish a representative LRV. So we wanted something that could be easily rejected by the system. So it should be similar in size to virus, which is the smallest of the pathogens. So something like MS2 or there's some even smaller viruses than that are around 30 nanometers in size. Some of the dyes are quite smaller than that, so they tend to be in the hundreds of molecular weight size compounds. Tests should be operated at the maximum operating flux, so where the membranes are most stressed, to ensure that even under the harshest conditions we're getting good rejection. And we've got to be able to detect very low concentrations of our challenge particle in the permeate. So if you think about detecting 4 log removal, that means you're rejecting 99.99% of what you put in. And we can't afford to put in very high concentrations of these challenge particles into the feed water because then it becomes too expensive. So typically we're looking to get a treatment cost of 1 cent per cubic meter or less, which means we're really limited to about 1 milligram or maybe 10 milligram per litre if we're not adding continuously. And so what this slide is showing is that if we're adding 1 milligram of litre in the feed, then to get a log removal value in the concentrate of we're having to get down to detect down to 1 nanogram per litre or less in order to be able to do that. So you need something which you can detect at very small concentration. So you need a very sensitive detection system, and that's really critical to verify these high log removal values. So for the selection criteria, it has to be similar size, similar shape to virus. As I said, you have to be detectable at very low concentrations, has to be stable under the operating conditions. So for fluorescence, we know that's affected by salt concentration. So if we're using RO membranes, then we can get quenching of the fluorescence. So we may have to make some correction for that, or it may make it not a very good test. So it may not be accurate. We don't want to react with anything. Certainly should be non-toxic. We don't want it to foul the membrane, so non-absorption. And as I said, very inexpensive. So quite a lot of challenging criteria for us to aim for. Here in this first bit of work, we looked at a range of dyes main one being rhodamin WT and some other ones there, and also some commercial nanoparticles that had a fluorescent dye tag to them on the outside. And we screen them over a range of operating conditions. So as I said, the salt can quench fluorescence, so we wanted to have a look at that. You might have oxidants in there which can also start to decompose the dyes or the nanoparticles, as can UV light. And then if we get fouling on the membrane, we can also see some interaction with the fouling layer, and or potentially see that between the fouling layer and the compounds that we're adding. Key findings for this was that rhodamin WT was certainly better than those other dyes that we used, and a lot better than the commercial nanoparticles. So here you can see this is the nanoparticle here, and this is the fluorescence intensity that we get versus the concentration we have to add. So to get a high fluorescence intensity that we need for detecting the very low concentrations, we need to add a lot of nanoparticles, but very small amounts of the dye. So this gives us an advantage over those commercial nanoparticles. There was also some interaction with hypochlorite for some of them, but rhodamin WT was sensitive to hypochlorite and UV, but not really sensitive to pH or conductivity, so the amount of salt in solution. So from that perspective, it was very stable. So that was promising. If we do some bench scale testing, the nanoparticles, we could really only get a log removal value verification of about 1 to 2 log removal values, so not very good. With the rhodamin WT, we were able to get it up over 4, and we tried that on some compromised membranes, and we could detect differences, but regularly getting between 2 and 5 log removal values detected. And this is for reasonable concentrations in the feed stream of rhodamin WT. So in this case, 5 parts per million. In order to get that concentration of rhodamin WT down, the amount of rhodamin WT down, we thought about doing a pulse test. So when we do a pulse test, we can add a higher concentration of the dye or the challenge particle in the feed, and that way we have a higher concentration going through, and we can get more sensitivity in the rejection of that compound across the membrane. So we're measuring the amount of, in this case, rhodamin WT in the feed and the amount we detect in the permeate, and calculating a log removal value from that. And with the pulse test, where we can use, in this case, up to 10 parts per million rhodamin WT, we're getting, in this case, it's not showing so high, but in some other slides, I'll show you we get an increased sensitivity. But with a pulse test, we wouldn't be adding that continuously. So this is if we wanted to add it at certain periods during the day. So in this case, we're thinking we might only do the test 3 or 4 times a day. Not as good as continuous online detection, but similar to what we would do with the pressure decay test currently for UF membranes, where we might do that once a day on an industrial scale. So what it shows, what that work was showing, that rhodamin WT was quite good in terms of performance in what we wanted to achieve. Where it wasn't so good is there's not a true surrogate for virus, so it's very small compared to a virus. And if we think about the way that reverse osmosis membranes deteriorate, one of the ways they can do that is through aging of the active layer, and they start to let more salt through as their pore size or their gets a bit bigger, and it only has to get large enough to let through the dye to now start to register low log removal values, whereas that deterioration of the membrane may not be sufficient to really let through virus. So it depends on how the membrane's starting to fail. The nanoparticles are more realistic size to that of virus or the pathogen, but they're very expensive, have lower stability, and weren't so good to use. One of the things that our colleague Eddie Stasovich did was to make some other nanoparticles that had some unique optical properties, and we could use a different technique to detect them. It was an optical technique which could demonstrate up to 7 log removal value with relatively low phi concentration, so in that 1 to 10 milligram per litre range. And certainly the cost of making them was nowhere near the cost of the commercially dye tag nanoparticles. So this is something we're investigating for commercialisation and looking to do some full-scale trials on. And so we did some additional work with Joe Jackangelo in the US on some rhodium and WT, and then some different dyes. So uranine, which was one that UCLA had looked at, and then Tracer, which is a commercial dye used for membrane integrity monitoring, sold by Nelco. And so that's another dye that's in the market. And comparing that with MS2, which is the traditional standard, and our new nanoparticles. And we did some pilot work in the US and then some in Tasmania as well. So this is just a bit of a look that if we didn't want to add anything to the water and just use water quality parameters, what we could actually expect to achieve there was no greater than 3, and most of the time around 1 to 2 log removal value. Some people do use sulfate, and it's not shown here, and sulfate with certain wastewaters you can get up to 3, but it's very dependent on the concentration of sulfate coming through in the wastewater. It's also done offline, so it's not something you can do online. So we didn't think that was a particularly good technique. It's reasonable, but it does require some additional work with a lower sensitivity. Again, we looked at water quality parameters and how they affected those 3 dyes. Again, the rhodium and WT worked, came out as being a very good performer against most of those water quality parameters, except for the hypochlorite, which tends to react with. Uranine wasn't so good, so it's quite sensitive to salt, so it tends to suppress the fluorescence and some of the other parameters as well. But Tracer was also quite good. So this is the Nelco sold dye for membrane integrity monitoring. We did some bench scale testing, and certainly, you know, the rhodium and WT and Tracer, we got higher log removal values that we could detect with those dyes compared with uranine. And when we did the pulse test, again, we can see increased sensitivity doing that. And that's using a pulse dose of 5 milligram per litre. When we did the pilot scale test, so this is in the USA, we're using 4-inch membranes, some Dell Filmtech brackish water RO membranes, and we're using some ZAPS detection system, but we're challenging with MS2 conductivity. In this case, Tracer. We did try the other ones as well. I'll just show the Tracer results and our nanoparticles. When we did this test, we got Dell Filmtech to make some membrane modules with defects in them. So we had one that had no defect, one with surface scratches, one with a point source leak that was made, one with an insertion point next to the pin. Then we exposed one to chlorine to wear the surface of the membrane down, the active layer, and start to get some TDS coming through. And then we also cut an O-ring. And actually O-ring failures are one of the common failures for RO membranes. And so here you can see the results of that. So we're comparing MS2 in the blue, conductivity verification in the red, and the tracer dye in the green. So MS2 is the one is our gold standard. So we know with that one it's similar in size to virus, and we believe it behaves in a similar way to virus. And we can detect high log removal values with it, in fact higher than the other techniques. And while we can detect it with that, we're not keen on using that all the time, because you have to grow the bacteriophage up in the laboratory. You have to take them back to the waters back to the laboratory to do the detection of how the concentration in there. So it's quite a laborious approach, and we've had some cases where you can't actually rely on the laboratory to deliver the bacteriophage when you want it, because if they have some problem in the laboratory, they actually can't grow it up in time. So not easy to use as a regular monitoring technique, but certainly when we're able to use it, it's the one that we think delivers a rejection value similar to virus. You can see with the red ones, with conductivity, always extremely low compared to the MS2, so it's a very conservative measure of integrity. And you can see with the chlorine damage, we're letting through most of the conductivity, but our rejection of MS2 is still quite high, up at 5 log removal values, so not really giving us a good demonstration. And in this case, we would be saying we need to get rid of the membranes, whereas we're actually getting good pathogen rejection. And so something like nanofiltrations would give you that sort of arrangement, those sorts of results. So low rejection on conductivity, but high rejection on MS2 or for virus. With the dye, the tracer, which is a bit bigger than salt, we can see we get higher log removal values detected. And so we can verify that, verify the membranes to a higher concentration or higher log removal value. It's still conservative against the MS2, so we don't want it to be showing a higher log removal value than what we get with the MS2, because then it would be giving us more confidence in the membranes than what we should have. And even with the chlorine damage, we're getting some rejection. What we would expect with if we did a nanoparticle test on this arrangement here, where we've got the chlorine damage, is that we would get something similar to what more similar to the MS2 than what the dye is giving us, because the nanoparticles are a larger particle and can be more easily rejected. We also did something similar on a pilot plant in Australia, again with some mixed dyes, and I better hurry up. And here just showing the arrangement. So we had some reverse osmosis elements, and we could detect rejection across each element and across the whole array of elements. And again, these were all intact except one had a cut O-ring. And this is comparing the 3 dyes, the tracer, the uranine, and the rhodamin WT. What it's showing is the rhodamin WT had the best sensitivity, so it always gave us the higher log removal value. So we were thinking that's the best dye. Nelco, when they sell their tracer, they also like you to use their detection system. We weren't using it, so maybe they can get better detection with their system than what we could. But, we generally saw lower log removal values than the rhodamin WT. And, when we have the cut O-ring, we see the decrease in all the rejections there, so low log removal value. When we compare that with the MS2 and nanoparticles with rhodamin WT, again, we see the MS2 gives us the highest log removal value. So the dye and the nanoparticle are more conservative, which is what we want, but we'd like them to give us the highest log removal value that we can. And we can see with the nanoparticles, we're actually getting better performance than the rhodamin WT in terms of being able to verify the log removal value across the membrane. not only do we get the high log removal value, but we see lower error. So you can see with the error bars, so these are repeated few tests, and we can see greater variation with the rhodium and WT than what we see with the nanoparticles. So quite happy with the performance of the nanoparticles. And so here you can see we're getting, you know, MS2 around 6, and with the dyes around 5. We're using conductivity during those tests, and when we're measuring that, you're only getting around 1.8 log removal values that you can use for verification that the membrane's intact. So you can only be credited with that value. So very low. So in summary, you know, the tracer and the rhodium and WT were capable of giving high log removal values at the bench and pilot scale. The pulse dosing gave us slightly higher log removal values that we could verify than the continuous dose, but you do need to put higher concentrations in the feed. So you can only use that intermittently. The pilot scale test results resulted in LRVs for MS2 and nanoparticles and rhodium and WT that were quite high, but much lower for conductivity. And where, you know, the nanoparticle that we're using is around 30 nanometers in size, so much closer to the size of a virus than a nanoparticle. So we believe that will give us better representation of virus rejection than what the dye does. But overall, you know, I think water recycling and the need for water recycling will continue to grow. So climate change is happening, and it is affecting our water resources. So expect to see growth in water recycling. Membranes will be important in that process because they can be used efficiently to remove pathogens. To get the best out of them, we need good integrity and good performance during service, and that means their mechanical properties and their wear properties become quite important. So something as researchers that we probably haven't focused on much, but something which is very important. You know, we've been demonstrating the membrane pathogen removal performance of online techniques, and it's currently challenging, but we think the use of nanoparticles can better simulate those pathogens and give us an online technique to achieve or to verify those high log removal values that we know an intact membrane can achieve. So thank you very much. I think I've gone over, but I'll hand you back to Dr. Lau.
Yeah, hi, Prof. Thank you very much, Prof. Stephen, for very interesting presentation. I hope our audience are enjoyed with your presentations. There are a few questions from our audience. I will read it for you. The first question from Mohammad Afizi is asking, will integrating activated carbon with microfiltration membrane improve LRV?
Okay. It could do. So I'm just trying to work out how to interpret this question. So, and the reason for that is I have seen people use activated carbon to measure membrane integrity of microfiltration membranes. So if you have a very high concentration of the activated carbon in the feed water and you're using the membrane to separate that, you can get you can use it to measure log removal value across the membrane. I don't think you can get up to 4 log removal value, or it's very difficult to do that. But if you're using activated, so I think as a technique for measuring log removal value, you could use it, but I don't think you'd get the same sensitivity as what we were aiming for. I think maybe improved, maybe more than 2 and maybe up to 3. If the question's asking, would the use of activated carbon going onto the surface and fouling the membrane improve the log removal value? Yes, I think that's certainly true. So one of the other projects we've worked with is looking at verification of membrane integrity in MBRs. And we know that when we have an MBR in operation, you have a very high concentration of biomass. And so if you do get a membrane that fails, it very quickly actually gets plugged with biomass, and then the membrane becomes achieves its rejection characteristics again. So I think something similar with activated carbon could be possible, although we haven't actually done that work. But I think fouling generally helps the rejection of all types of things across the membrane.
Okay, thank you. There is a second question from the same audience. He asked, will the ionizing the water before flowing through the membrane improve membrane integrity and as well as improve LRV?
Will ionizing or deionizing the water before? So I don't think so. So if you're talking about having deionizing, so removing some of the salt from the water, it might make the water, you don't have to worry about rejecting the salt to the same degree. But in terms of pathogens in there, I don't think it shouldn't change the rejection of pathogens. So really what the way you're getting the pathogen rejection is through a breach in the membrane, and if it's a high pressure membrane, then you're looking for a defect around the size of 30 nanometers or greater. So changing the composition of the feed water in that way, I don't think will change whether or not you have a breach of 30 nanometers or not. If you're doing a test with MS2, then one of the things you need to verify is that you actually have the MS2 well dispersed, so they're not clumping together. I don't think the ionizing or deionizing would actually affect the clumping together of pathogens in the water, but it's not something I've looked at in great detail.
The third question is the membrane made from synthetic material or organic or inorganic materials?
Okay. Sorry, I should have said we're just using standard membranes. So in the reverse osmosis examples, we were using Dow Filmtech RO membranes, so BW30s. So they're organic membranes, not inorganic materials. And there's no inorganic desalination membrane on the market that I'm aware of. You might have some nanofiltration ones, but not really rejecting salt. But again, those synthetic ones, those inorganic ones, if you're using them for pathogen removal, and some of them are down to that size, very hard to detect their integrity online at the moment. You'd have more confidence that they're working well. But we have done work with inorganic membranes on that plant in Tasmania. So we're using the ceramic MF membranes. And again, we were having to contend or be satisfied with just achieving a 2 log removal value across there based on their size and pressure decay test. So we still had to use a pressure decay test to verify that performance. If you're doing that with an NF membrane, an inorganic one, so just very small porous one, you would have to go to very high pressures in order to be able to do that. So, yeah.
Yeah, okay, thank you. We have one more question from Dr. Liang. He was actually graduate from University of New South Wales, Sydney, under Wiley.
Okay. Yep.
It's more on modeling. And he asked you, do you think there is a little opportunity to chemically modify the spacer surface to reduce the fouling for spiral wound membrane reverse osmosis? Current spacer coating seems to have very little impact on reducing fouling, although the present spacers actually enhance membrane biofouling.
Yeah, a lot of debate about this one, whether the spacer makes fouling worse or not. The ability of modified spacers to improve fouling. So some people believe the fouling occurs on the spacer. Other people believe it occurs on the membrane surface. And it might depend a bit on how you're doing your tests. It's not an area where I've personally done a lot of work on, but I know that there has been work done on this to look at how to maximize the turbidity, so the spacer geometry to maximize turbidity with the lowest pressure drop, and it seems to have some good results. I think Hydronautics actually sell a spacer that has a antibacterial coating, so something that prevents biofouling growing on the bacteria. I think it has some improved performance, but I've only really seen the data from Hydronautics, not some independent data, so it'd be good to have a look at that. So I think chemically modifying the space is certainly an area of interest. Getting it in, I would have said a few years ago that getting into the market, the biggest issue would be the price of that. But given the Hydronautics have actually got one in the market, you know, I think maybe there is opportunity to do a bit more work on that. So I think they've used things, cell signaling technology to prevent the growth of the biofilm on the surface. But you know, you might find that sometimes it works and sometimes it doesn't, because I don't think we really got good consensus on how the biofouling works. And you know, I think that area's got a bit more work to go in order to clarify some of those issues.
Okay, thank you. Prof, personally, I have one question. Do you know any company they are selling nanocomposite ultrafiltration membrane in the market?
Ultrafiltration? No, I don't. No. So certainly there's the one RO, LG seller, the nano H2O membrane, so nanocomposite one. But I don't know if anyone's selling ultrafiltration membrane, no. Okay. And you know, so we did that work with Memcore. And it was really aimed at, you know, improving the wear characteristics, and we were set out to look at seawater applications, because in seawater you have more abrasive compounds or sand particles in the water that are more abrasive than the organics you find in water recycling. But in the end, what Memcore did is they didn't bring out a nanocomposite membrane, but they did bring out a different style of polymer membrane that was more abrasive resistant. So there are some other characteristics of the membrane that can also help wear resistance without having to add the nanoparticles.
Okay. I can see from the chat board there's no more question, and most of the audience, they say hi to you and thanks you for sharing. So I think I will pass the event back to the Dean of the Faculty, Professor Rafiq.
Sorry, I went a bit long.
It's okay, no problem. Lauwiji, thank you so much for moderating the session. And to our distinguished speaker, Professor Prof Gray, thank you so much for sharing all the information regarding the membrane and its applications. And thank you again for accepting our invitation to speak at our UTM Engineering Distinguished Lecture Series. And to all of you, our viewers around the globe, thank you for watching. Do stay tuned because we have many more lecture series for you. Until then, bye-bye for now. Bye-bye.
Bye.
Bye-bye.